So, we have a double header today of local talks. Our first speaker is Zheng. He's going to be telling us about exploring emergent phenomena across measurement level. So, please take it away.
Good afternoon, everyone, and thank you for the introduction. My name is Zheng. I'm currently in DGG's group and also Charlotte Borchers group as a postdoc. It is my pleasure today to share with you some of my past and ongoing research. And I know that 30 minutes is a short time, so I want to take actual advantage of this in-house setting to give you more of an overview or more like an advertisement talk to give you some sense of idea of what we're capable of and in hope of fostering some potential collaboration within the audience here. So yeah, coming from a condensed matter background, I would like to first address a basic yet important question. What is condensed matter physics and what do we care about as a field? So I think it can be thought along with two other fundamental branches of physics, namely cosmology and particle physics. For cosmology, they care about extremely large, namely that they care about the scale and the history of the entire universe. On the other hand, for the particle physics, they care about extremely small, like fundamental building blocks like the quarks, electrons, and the forces in them. But for condensed matter physics, we care about the extremely complex, meaning that we care about how many of the particles, when they come together, when they interact, give rise to entirely new phenomena that you could not have been predicted based on just looking at individual parts. So in a sense, condensed matter physics is all about emergence, how the properties of the atoms and interaction between them give rise to the macroscopic behavior of the materials. So let me give you a few examples. So in ferromagnetism, we know that the tiny moments that electrons spin, when they align themselves, they give rise to a macroscopic phenomenon that we know as the magnetism. And for a superconductor, despite being both negatively charged, electrons then come together to form a pair. And you can give rise to something truly strange, like a superconductor levitating above a magnet. And when an electron and a hole come together to form a bond pair, and when they recombine, they will emit a photon, and that's the basic principle behind luminescence and many of the optoelectronic devices. Therefore, collectively as a field, we are constantly hunting for a new state of matter, and that a lot of times requires us to have the capability to manipulate the material and probe them in various different techniques and measurement approaches. And by connecting the dots between the macroscopic and the macroscopic world, we're trying to find universal principles that can allow us to draw the conclusion of how different materials can behave similar ways. For example, like nuclides and can behave similarly to the group rates. So from my perspective, my research experience kind of really echo this broader themes. In these past, current, and future experiments that I'm involved with, we're really trying to dig out emergent phenomena rooted in the complex interplay between all the fundamental particles. And each of these phenomena are reviewed by different experimental techniques, ranging from DC all the way to microwave regime. In particular, towards the end of the talk, I would like to introduce some of the current projects that we are working on that really take advantage of the tools from the quantum community and try to apply them to the study of condensed matter physics. And in particular, in each of these cases, where our goal is to try to combine or really dig out the connection between the macroscopic phenomena that we observe experimentally and the microscopic physics that we can understand of. And on one hand, this allows us to study a lot of the a simple material system through a different experimental approaches so that we can study the different properties of the single materials. But on the other hand, it also opens up a wide possibility, meaning that these techniques can actually apply to many of the materials beyond a single class of materials. But so one thing that is really amazed me is that a lot of these different phenomena that we observe actually come from one simple material, namely something that come out from the lead from our daily pencils. So basically, when we write with pencil, what we are really doing is that we are scraping off thin graphite. And when we try to isolate one single layer of graphite, we get graphene. And in my study, we care about double bilayer graphene, meaning that we have two sheets of carbon atoms stacked on top of each other. So, but for bilayer graphene, without any of the external perturbation, it had this characteristic parabolic band dispersion where the conduction band and the valence band touch each other at the charge neutrality point, which is this depth line. And when we try to apply an electric field across the layer, we can polarize the electron towards the one layer and create this electric potential difference between the two. And if we reverse the electric field directions, we can also reverse this layer polarization. And one of the consequences of this layer polarization is that it breaks the inversion symmetry that originally have within the systems and create a layer polarization and electric potential difference between the layers. So in the following slide, I'm going to use this Y star to represent these particular conditions where the system presents an inversion symmetry, meaning that if I invert the system around this point, you map back to itself. So in order to prove the electronic property of bilayer graphene, what we do experimentally is that we encapsulate the bilayer graphene with boron nitride, which serve as dielectric. And then we can make the electrical contacts to that, which allow us to flow a current and measure the voltage across them. In addition, we can add a top and bottom gates, which allow us to tune the charge carrier density and the displacement field of the system. So what we normally see within when we try to measure the electronic property of the system is that we can measure the resistance as a function of the gate voltages. And along this diagonal line represents the charge neutrality. In particular, this Y star, as I mentioned before, represents the condition where the system retains its inversion symmetry. And for a normal bilayer graphene, if we sweep the gate forward and backward, we'll see a charge neutrality peak here and manifest as a resistance maximum. However, this is in direct contrast to a case when we control the relative twist angle between the top and bottom B end to be 30 degrees. And in this case, we actually observe a prominent hysteresis and we sweep the gate direction. So here I'm showing a resistance difference map taken between a forward scanning direction, which is in the red color, and the backward scanning direction, which is in the blue color. And this prominent hysteresis can also be seen in a line cut, where the charge neutrality position will shift depending on the sweeping direction in the forward and backward directions. So this kind of hysteresis as a function of gate really reminds us of ferroelectric materials, meaning that a system can spontaneously develop a electric polarization, which is also switchable depending on the electric field. So in order to understand our system, it is natural to study its behavior as a function of charge density and the displacement field. So here again, I'm showing a resistance difference map that taking between the forward scanning direction, which is the yellow / red color, versus the backward, which is the blue color here. So again, if we try to locate the Y star, which represents the system being at inversion symmetry, then it happens at this particular location for the forward and the backward direction. And now if we focus on the forward scanning, which is this line, and if we look at this particular location at d equals 0, we see that the system has already developed a finite resistance, meaning that it opens up a band gap, which also implies that there's a layer polarization and electric difference between the two layers. However, at this particular location, we're at 0 displacement field, meaning that we're not really adding any electric field externally. So, but the fact that we have observed a finite gap opening implies that in this system, there's an intrinsic electric polarization that sustains this layer polarization. What we can do next is that we can take a line cut at n equals 0 and study its behavior as we sweep the displacement field. So with a small range of displacement field, what we can observe is that the forward scanning and the backward scanning overlap with each other, and there's no hysteresis up here. And once we exceed the critical electric field, we can start to see the hysteresis loop to start to develop. And more importantly, this hysteresis loop size can actually vary linearly with the displacement field range. And as I previously mentioned that from the data itself, we can imply that there's electric polarization developed within the system. And the fact that they can vary continuously, meaning that we have a spontaneous electric polarization that have a continuous scalable magnitudes. So in order to try to understand this behavior, we employ a phenomenological model inspired by the Prusak model of hysteresis. This is a very general phenomenological model trying to describe any system that has hysteresis, for example, ferromagnet or ferroelectric materials. And it can simulate this system as composed of many of the hysteron, meaning that they are composed of like tiny hysteresis loop like this. These are the individual switching units. And each switching unit has a critical displacement field, DC1 and DC2. And in a traditional software electricity, meaning that the polarization has a displacement field dependence like this, all the hysteron distribution will follow this Gaussian distribution within this quadrant of this parameter space. However, and this difference between like we have bigger loop and smaller loop, it all comes from the different domain within a system, meaning that it only requires a smaller electric field to switch this particular unit, and it requires a larger electric field to switch this particular unit. However, for our systems, our polarization dependence as a function of displacement field looks something like this. And in order to capture this behavior, we find out it actually requires a very discrete set of hysteron, each with identical shape, meaning that the size of this hysteresis loop is fixed, and the center of this hysteresis loop is evenly distributed along this line. And only this particular distribution or this unit set of hysteron will be able to reproduce the polarization dependence that we saw previously. And so in the natural material, it is hard to imagine that how we can have different domains of identical size, but their critical electric field can be different from each other. And so that we seek an alternative explanation. And one natural candidate is actually this type of dipolar excitron, meaning that the electron and hole are spatially separated. However, they serve as the most fundamental electric dipole, meaning that the negative charge and positive charge will generate a small electric dipole between them. And if we now look back at our experimental data with this hysteresis loop, and we focus on this original point. And at this particular point in the whiteboard scannings, we see that there is a finite electric polarization developed here, and it can be explained by these layer-separated electron hole bound pairs, which itself can support a electric polarization across the layers. In addition, the opposite configuration of these electron hole bound pairs can give rise to the opposite sign of the electric field, which allow us to have these switchable electric polarizations. In addition, previously I mentioned that the electric polarization itself can be linearly tuned and its magnitude can be scalable. And that can be explained by the number of basically these electron hole pairs within the systems. And similar to all the ferroelectric materials, all this electric polarization has a non-volatile nature by itself, meaning that we can program our system with this electric field pulses and switch them in between the up polarization and down polarization. But differ from the traditional like ferroelectric material, which only have very limited number of polarization states, our system can actually have a continuously tunable polarization state, meaning that by varying the electric field pulses, we can program them into different states. In particular, if you try to zoom in a particular displacement field range, we can resolve finer and finer distinct polarization states. And if we within this particular electric field range, we can just go to any arbitrary states by programming them through a sequence of electric field pulses. So this has a is quite beneficial for all the memory applications. But beyond that, there's actually a very neat application in the field of neuromorphic computing. So for neuromorphic computing, it means that we're trying to mimic how our brain functions, meaning that we're trying to operate in a very high energy efficient way. And the basic principle is try to find an element that can mimic how the neuron operates. Basically, in our brain, the different neurons are connected by these synaptic synapse. And the synaptic weights it characterizes how strong the neurons are connected. So in this case, we can model our systems with a top gate and a back gate as a presynaptic neuron and a postsynaptic neuron, and use our conductance to characterize the synaptic weights, meaning the connection strength between the neurons. And by applying different electric field pulses, we can realize this very characteristic behavior of how our brain functions, meaning that we can potentiate our system and depress our system just by repeatedly pulsing our system. This mimics how our learning curve and of our brain, meaning that if we try to practice a action repeatedly, we'll remember it more strongly. And if we have a neglection of this kind of practice, we'll forget this action just over the period of time. And traditionally, this kind of fundamental building blocks of neuromorphic computing is actually relies on tunneling junctions of insulator, and that requires a large power and large voltage to operate. But benefited by this transistor kind of geometry and the low and high conductance of this graphene system, we're actually realizing a synaptic transistor that enables a low power and also bioheuristic synaptic function for neuromorphic computing. So all these findings from turning the bilayer graphene into a ferroelectric materials is actually not limited to one single material system. And in fact, it actually leads to a wide class of van der Waals synthetic ferroelectric materials. In particular, people have found that this layer separated quantum dipoles is believed to give rise to this microscopic electric polarization that is similar to our picture that I mentioned before. So that's basically the first example that I want to demonstrate, where we apply an AC signal across our device, and we measure the linear response of our system, which will reveal a hysteretic behavior within this particular geometry of the bilayer graphene and BN heterostructure. But in the next example, what I want to demonstrate is that we are still applying AC current at the DC limit, meaning that it's only a few hertz, but we are measuring the second order response, meaning that we are probing the frequency at twice the frequency that we are applying. So here, we're going to start from a broader perspective. So classically, when an electron moving in a magnetic field, you experience a Lorentz force that is perpendicular to its direction, velocity directions. But quantum mechanically, the self-rotation of this wave package will have an internal angular momentum, which will lead to a transverse direction. And this is governed by a quantity that called the Barry curvature, which acts as a magnetic field in the momentum space. So we know that for the linear anomalous Hall conductivity, and in particular for in a 2D insulator, if this system breaks the time reversal symmetry, then the linear Hall conductivity is governed by the integral of the Barry curvature over the Fermi surface. However, a nonlinear version of this can actually exist in a system that has broken inversion symmetry, but preserve the time reversal symmetry. And one particular example here is the Magnus-Hall effect, where the self-rotation of the electron wave package can actually develop a transverse direction in the applied current direction. And as its name suggests, the Magnus-Hall effect here is similar to how the self-rotating of a tennis ball develop a transverse directions. Here we can understand this picture semi-classically, meaning that with this electron moving in these directions, the Barry curvature that it carries will give rise to a transverse directions perpendicular to its velocity directions. So therefore, intuitively, we can understand this Magnus-Hall current is governed by the sign of this charge carrier and the sign of the Barry curvature in the applied bias directions. So in bilayer graphenes, at the low energy levels, we have this parabolic band dispersion, and if we take a line cut of that, we can get this isotropic band dispersions. And we have both K and K prime value. And as I previously mentioned, when you apply electric field, we can open up a band gap and so that the layer can gain a layer polarization. In addition to that, it actually carries the opposite sign of the Barry curvature between the K and K prime value. And here, this particular effect only samples the right mover, meaning that we are actually only care about this integral of this partial integral of this Barry curvature at the Fermi surface. But we have both K and K prime contribution. If we add them up together, you give rise to a zero second order conductivity. But in reality, when we open our band gap at bilayer graphenes, at the low energy, there's this least transition that will trigger a trigonal warping of the Fermi surface. this leads to this anisotropic distribution of the Berry curvature. Now, again, if you try to select the right member, then the sum of these two parts, the k and k prime value, will not be zero. Therefore, we can actually expect a non-zero second-order conductivity that can arise from these systems. So in terms of experiments, what we're doing is that with SEM, we are making this sandwich device composed of BN, bilayer and BN. But here we're making a lot of context, and the reason will become clear in just a moment. And if we try to measure the linear response, you can see a normal bilayer graphene behavior where we can open up a gap with applied electric field. Now, if we try to measure the second order response, meaning that we apply a current along this vertical direction, and then we measure the second order response in the perpendicular directions, we can actually measure a very prominent second order response. And if we try to measure this and this as a function of the excitation current, one has a linear dependence and one has a quadratic dependence, which confirm that the signal that we observe here is indeed second order in the Hall signal. So if you remember, I mentioned that the Magnus Hall current is governed by the sign of the charge carrier and the sign of the Berry curvature itself. So we can intuitively try to analyze whether our data makes sense. So here, if I try to put the line cut at a fixed density and measure its second order response as a function of the displacement field. So let's focus on the whole side first. In this case, here I'm drawing the Berry curvature distributions of one valley and as a function of the displacement field. At zero displacement field in this particular valley, let's say just call K valley, it has zero Berry curvature. And if we apply it one side of the electric field, it opens up a band gap. And at the band edge, it picks up this Berry curvature distribution that we call as a Berry curvature hotspot. And in this case, we are looking at the whole level. And as we vary across the displacement field net smaller than zero to larger than zero, we're actually switching the sign of the Berry curvature. So therefore, we actually observe the sign switching in the second order response. That's consistent with this picture of the semi-classical picture, where with the same type of charge carrier, but with the different sign of the Berry curvature, it will actually lead to a different direction of this trajectory. Now we can fix the charge density, fix the displacement field and study its dependence as a function of the charge density. In this case, as we vary across the conduction band and valence band, the Berry curvature will switch its sign. However, there's another row here, which is the sign of the charge carrier also switches. So meaning that we are converting from a electron to a whole sign. And so therefore, we have two negative signs which will lead to a positive sign. Therefore, we expect the same sign for both holes and electrons for the second order response. In addition, as I previously mentioned, that we are in this particular effect, we're only sampling partial integral of this Fermi surface. Therefore, it depends on the current direction that we're applying. We're actually sampling different area of this Berry curvature at the Fermi surface. Now, if I switch the direction of the current that I'm applying, I can expect a different response from in the second order channel. And that's indeed what we observe experimentally. But we can take a step further because we have a lot of context within our device. So therefore, we can measure this response as a function of this really the angle that we are applying our current. And the angle resolved in this second order response actually reveal a threefold rotational symmetry of the underlying Berry curvature that I previously mentioned. If you remember that the trigonal working will lead to an anisotropic distribution of the Berry curvature itself, and this itself has a threefold rotational symmetry. And we can actually extract this information based on the angle dependent measurement. So really, this effect is sort of a second order or second harmonic generation, but in the DC limit. Second harmonic generation is no stranger to us. It first being implemented in optical regimes. However, this requires a large band gap. By pushing this effect into the DC limit, we are actually sensitive to the property at the Fermi surface, which allow us to really probe the quantum geometry information at the Fermi surface. And combining with scanning probe technique and the in-situ rotation, we can really realize a fine angle rotation, which allow us to extract the fine resolutions of this Berry curvature distribution at the Fermi surface. So now we're done with basically the DC transport. We're moving up the frequency range where we're moving to the hundreds of kilohertz to megahertz region. In this experiment, we're doing a penetration measurement, meaning that we're treating the top gate and the back gate as the two parallel plate capacitors, and we're measuring the compressibility of our systems as we vary the electric field and the density of our system. So just a reminder again, here for the bilayer graphene at the zero displacement field, we have the band touching, and with a finite electric field, we're opening up the band gap. So this can be directly reflected in the compressibility measurements, where for when the system becomes incompressible, we are seeing a large signals here. But in addition to that, in the second example, I showed that the trigonal warping, where the triagonal distribution of Fermi surface give rise to a second order response. In this third example, we're actually focusing on this maximum of this density of state. This is because when we're moving from this, moving across these transitions, there's a point where the Fermi surface actually diverge, and therefore, actually, the density of state diverge, meaning that at this point, the electron-electron interaction is enhanced. And at this particular point, you actually lead to a series of symmetry broken states. So for bilayer graphene, it has this different favor symmetry, like, for example, the spin up and spin down. And as I previously mentioned, we also have the K and K prime value. So generally, these four favors are degenerate with each other. And we only see that this fourfold degenerate Fermi surface. However, at this particular point where the density of state diverge, the electron-electron interaction can drive the system into this spontaneous broken symmetry state. And what it manifests in terms of the experimental data is that when we try to measure the compressibility of this system as a function of the density and displacement field, we actually see this dark feature, which is actually a negative compressibility, which signals the phase transition of our systems. What we can do is that we can measure this basically the Landau level distributions of at the finite magnetic field, and looking at these different regions here, the dashed line is basically marking out the different phase boundary here. And in this case, we observe a synchrotron orbit that has a different spacing within different region of this map. And we can do it more quantitatively, meaning that we can measure the quantum oscillation as a function of a magnetic field and do a Fourier transform, which allows you to directly extract the information about the Fermi surface. So for this particular region, we have 1-4, meaning that all the 4-4 favors are degenerate, meaning that all the spin and varied degree of freedom are degenerate. However, in this particular region, we have 2-4 degeneracy, meaning that the system is either spin polarized or valley polarized. And in this particular region, all the favors are broken, meaning that it is simultaneously spin polarized and valley polarized. And what's interesting about this is that that in this space boundaries, other studies actually show that at this particular phase boundaries, when they cool down to lower temperature and apply an inclined magnetic field, they can actually observe a superconductivity within this system. Then the question is whether we can bring this kind of superconductivity into a zero magnetic field regime. And the answer is yes. Another study shows that by combining the bilayer graphene with the WSC2, they can actually see the superconductivity at zero magnetic field. And in addition, this spin orbit coupling can actually enhance the superconductivity, bring up the temperature by 10 orders of by a factor of 10. But nevertheless, like the superconductivity, like the nature of the superconductivity in either the bilayer graphene or the bilayer graphene combined with WSC2 is still remain a mystery. And that leads to like my motivation for the work I'm doing here is basically trying to take advantage of the probe that we have and combine with the techniques that we are familiar with in the quantum field to try to probe this the nature of this superconductivity. So we know that for superconductivity, its response to electric magnetic field can be characterized by this superfluid statistics. And for a S-wave superconductor, it follows a exponential dependence And for a nodal superconductor, it follows this power loss dependence. And this is quite obvious and evidence in the two-plane studies where they see a different dependence as function of dependence of the penetration depth as function of temperature. However, the challenge is that this kind of technique is inapplicable for the van der Waals superconductors. And recently, there are two approaches to solve this issue. One is based on the security platform, basically integrating the van der Waals superconductor in these alpha circuits and try to probe the resonant frequency shift as a function of temperature. And the other approach is based on the scanning SQUID, meaning that we can measure the susceptibility, which is related to the superfluid stiffness, which also allows to extract these informations. And this is only recently demonstrated in this MOS2 systems in the van der Waals superconductor for the first time. However, we're still battling with the sensitivity of this technique, meaning that in the 2D limit, the signal is very weak and it suffers from fluctuation itself. And one way to overcome this is through the RS SQUID, which is being developed by Elaine and Vanilla in the group. And here we're combining the SQUID with a capacitor to form a resonator geometry. And in this case, we can see the resonant frequency tuned by the flux to go through the SQUID itself. But we can take a step further by combining with parametric amplification, meaning that we can pump the system at twice the resonant frequency, which allows us to amplify the signal that we observe here, and it will give us a hope to detect this really fragile and weak signal in the van der Waals superconductor. Therefore, the goal is to try to implement this scanning technique with the superconductor itself. And just very quickly mention the last thing on the cavity measurement, where we're moving away from the van der Waals systems. So two sides. This will go through the time. 30 seconds. That is 30 seconds enough. So in the 2018, the twisted graphene is really picking up the moist superconductor, but around the same time, we have also the Zhiren-based superconductor, which shows the candidate for spin-triplet superconductor. And there's a prediction of a collective mode within this spin-triplet conductor. And here, what we're trying to do is try to probe this collective mode through a cavity technique that first developed in Davis' group. And here, in our group, Sam, a student, developed this copper-based fluid cavity, which allows us to couple this cavity mode, like basically the
Let's give the speaker a warm round. You take your slides, and you can, if there's a question, we can take your question while the next topic is set up. Yes.
You happen to have like a microscopic understanding of the origin of these. Actually, by using the first
Wait.
You happen to have like a microscopic understanding of the origin of these like electrical dipoles. How they become interesting.
Yeah, so I think there's no concrete theory right now. So basically, this electric dipole is basically through the electrical injection, like how people have developed, have observed in the dipole exponent insulator in the MOID TMV system, where this dipole is injected through the and the stability of these exponent dipoles relies on the detail of the structure and how the alignment of this BN top and bottom BN create this local site to trap these points.
Thank you. All right. So our second speaker for today is Chao. Thank you for joining us. He's going to be talking about fast quantum computation and all the
Thank you, and thank you all for coming. So I'm a theory postdoc and mainly working on quantum antibody systems. Today, I'm glad to talk about these of my works. Feel free to interrupt with any questions. I don't need to go to the end of my slide. So let me just start with the question that I want to address. That is, how fast can all Hamiltonians, which I will define, how fast can they process quantum information, say generate antibody tangle states or some many-body unit. So when talking about like information processing, people usually think about like quantum circuits based on 2-qubit gates. But in many experiments, also including many of those exciting experiments happening on campus, these platforms usually have auto connections between the qubits. That is, like every pair of qubits are coupled by some equal footing. So given this like connectivity, we want to understand well how we better utilize them. And for example, a fast evolution will be good, especially for like the current generation noisy devices, because a small evolution time really means a small total error accumulated during the evolution. And also, I will focus on auto Hamiltonians, but you can expect the results will generalize to long-range interactions, where the interaction will decay with the distance, but as long as it decays sufficiently slow, then.
So when you say all to all, you mean I can choose who talks to whom, or I only have a?
You'll see the precise definition in the slides. So it's like I can choose arbitrarily as long as like each coupling strength is smaller than some constant. And in theory, there also has been a long history of studying auto Hamiltonians, where people want to use like point models of auto Hamiltonians for understanding physics, like spin glass, from gravity, etc. So here I kind of want to understand these systems from an information kind of perspective. Okay, so this perspective may be a bit abstract. So let me provide a kind of a canonical example for this, which is like, well, in like this spatially local systems from the Brown and Robinson, we know that local information can only propagate with some bounded velocity during evolution. And although it's a result of our time evolution itself, it turns out to imply like properties of many kinds of like many-body states, etc. For example, Hastings have used this to show that well, all gas ground states have short-range correlation, just like a very general structural property of many-body states. And interestingly, there's also like a proof today about like more fine-grained understandings of this. And so here, understanding like how fast a local information can propagate, like this information speed problem has been considered in recent years to generalize to this power law interactions. But prior to our work, it is unknown for this like strongly long-range interactions, what is the ultimate speed limit, which I will show resolve as resolve this problem. So, any question about the motivation? So let me just be very precise about my setup. I consider n qubits with this polymatrices xi alpha, and I allow my system to engineer any kind of this Hamiltonian H that can depend arbitrarily in time, can couple any pair ij qubits with coefficient j ij, can depend on alpha beta, as long as I choose a normalization that at any time this for each pair the coupling strength is smaller than 1. And for now, let's first consider the path of like starting from product state, like how fast can I use this time-dependent Hamiltonian evolution to generate, say, the many-body GHT state, like a state that encodes global information. And notice that here I will allow for constant space overhead, that is, I'm satisfied as long as I compare n over 2 GHT states, while the other n over 2 are as well as the start from the last state.
Sorry, but then how's it constant space if it's n over 2?
So it's like overhead is like the multiplicative.
Okay.
Yeah, so first of all, there's naive approach to this. You can suppose that because I know that well, starting from this product state, I can use this like gate-based quantum circuit to prepare the GHT state. Then I can just turn on the couplings between the pairs of qubits. I know that here the gates are actually commuting with each other, so I can just turn on them simultaneously, so that after some order 1 time, each coupling generates some 2-qubit gate. So that's at least I know that with order 1 time generate the GHT state. So it's already not that bad. But observe that well here, you have only turned on like order n couplings, but in my setup allow for n squared couplings. So you can expect that well, there are like more clever ways that I turn on all the counts that I can do much faster. Say I do like even n times faster. If you don't like this like time vanishing with the system size, you can consider well I choose a different normalization so that I'm asking well can I get some order one type instead of some protocol that grows with system size, which is the case for example for prep times. And there's indeed a nice prior work on this, which proposes one runtime protocol, but it only prepares some like GC-like analog state that does not have a very good fidelity with the actual state not to prepare. So here comes our first result. We prove that this so-called quantum gate, which is the circuit that prepares the GC state, it can be simulated by auto Hamiltonian protocol in one runtime. Although this is not exact simulation, the error decays as a polynomial in it. So usually it's sufficient for this. And this is asymptotically the best. So as some simple corollaries, first you can choose like there's a single I here, so that it means like with like n number of ancilla qubits, you can speed up any 2-qubit gates from order 1 time, that is from naive approach, to using one runtime. And as I said, this means gradient state can be prepared in this one runtime, but also you can show, for example, this many-body W state, that is the superposition of only one spin being excited. That state is also preparable.
In this time scaling, how you normalize your algorithm?
Yes, I just normalize by saying that each pair is bounded by 1.
Yeah, but in terms of the total interaction energy,
yes,
it scales with n, right? You are actually not thinking in terms of energy.
Yes, if you compare the total like Hamiltonian spectrum width, then that does not provide you advantage. But for example, for trap towns, you can choose to like whether you engineer some really spatially local interactions or really some like all-to-all interactions. And for all-to-all ones, although you have this like one-to-one suppression to make the whole like Hamiltonian strength equal, but with this all-to-all, you still win compared to this like local protocols where you have to kind of route information from one side to the other, which will necessarily give you like some size growing evolution time. So I think in that sense you can kind of and some other like corollaries. So this like multiply control topic gates can also be generated in one runtime. And this also solves this information speed problem for long range, so sufficiently long range power requirements that I mentioned, because it matches lower bounds on the time. So let me just give you like one slide of the intuition why you can do this. So here, I consider the system to be like one data qubit that starts from the plus state and all the other n qubits from here, and they will start from the zero state. And in the evolution, I will constrain the dynamics to be only happening in the so-called decay manifold of the n qubits or like the permutation symmetric subspace, which you can view as a semi-classical spherical phase space. So like, for example, the initial state is like some circle at the North Pole, where the circle means you have some quantum fluctuations along the x and y directions. So the protocol works like this. You first kind of want to squeeze the state so that the quantum fluctuation along, say, the y direction is sufficiently suppressed. Then you want to interact between the data qubit and the decay manifold to kind of, depending on whether my data qubit is in plus or down, I separate my wave packets in this phase space. And here you can see why I want to squeeze at first, because, well, if it is much smaller fluctuation, then you can move like with a very small angle to separate these two, and that basically gives you a 1/n angle to separate them, and that ultimately becomes the 1/n time in resource in my program. And then I still use this axis twisting, squeezing in the next stage, but here I'm kind of using its stretching axis. I want to kind of some exponentially fast way stretch the two wave packets so that after some 1/n time, they are moved to this 2 points, antipodal points. And I think this step may be the kind of miracle step for me. That is, well, it seems like previously you are doing something crazy, but even after that, the two wave packets are still like very well behaved. They still look very close to like the coherence squeeze state. So that afterwards, you can do some tricks to kind of unsqueeze the two parts so that we really become the trick system. And this is not the protocol that I proved that it works asymptotically, but this is a protocol that kind of works well quantitatively in the sense that here it works for thousands of qubits, which compared to convolution time compared to night circuit protocol by say 6%, and it also basically prepares the target state by infinite distance comparison. So, any question about this first result?
What's the scaling inability?
Yes. So for this protocol, I cannot prove anything. But for the previous one, you can. It's like you can evolve for some slightly more time to gain a better infidelity, which can be scaled polynomially, inverse polynomially with system size.
Does it have to be 2-axis twisting, or are any Hamiltonian that has like stable trajectory or
I would guess that any Hamiltonian that gives you some squeezing effect will work. But here I only tried this, and in my proof, I need to design some particular thing that I can keep track of analytically. Okay, so then I'll switch to the second part. You don't need to follow the first part to understand the following. So here, instead of like talking about some specific entangled states or unitaries, I want to do some kind of general purpose compilation protocols. That is, well, suppose you give me any quantum circuit, overall quantum circuit of depth d. How fast can I generate that unitary using this all-to-all Hamiltonian? Okay, so the naive approach can achieve this with a time t that is just b, where you can just turn on each coupling pair to generate that qubit gate at that time. But can do like much faster than that. So first, observe that the previous protocol does not give you advantage, assuming constant space overhead, because, well, for general all circuit, you can have like n simultaneous gates happening at the same time. And my first protocol can only like simulate them one by one, although each one is like 1/n time faster, multiplying with extra n, you get no advantage. So here comes our second main result, which is that, well, for any give me any depth d quantum circuit, I can design a Hamiltonian evolution, all-to-all Hamiltonian evolution HT, that simulates the circuit unitary with a time that is d over root n, like a root n faster protocol. Again, here there's an inverse polynomial small error, and there's also some minor remark that here I need some randomness in my Hamiltonian so that the protocol does not succeed always, but it succeeds with overwhelming probability for given input. So the next two slides, I like to sketch like how this protocol works. So basically, it comes down to simulating, well, how can I simulate like one layer of like order like n over 2 big gates in 1/√n time. So let's first look at the simple problem, which is, well, so here again allow for constant space overhead, so I can have like order n qubits. Let's first consider, well, what if the ancillas are actually boson modes? I have like n boson modes or like n harmonic oscillators. Then the problem can be basically solved by just performing a Fourier transform. Why? Because, well, suppose the original bosons have this analysis of the BA labeled by A is like 1, 2, 3, 4. I can just perform a Fourier transform to define another set of few boson analysis operators, B2 to K, labeled like K the Fourier. So that, well, initially I have like order n square couplings between the data qubits and the absolute bosons. After Fourier transform, I can kind of focus the coupling strength to only order n of them, but each of them being root n stronger, as we can check from this formula. So that, well, here is about generating some unitary that couples qubits and bosons, but you can use some like well-established Moore Thornton gates like approaches to use this Fourier boson modes to induce two qubit gates on the data qubits in one over root and time faster. Okay, so what about my original problem that is only for qubits? Well, my claim is that, well, you can basically do the same thing. You can Fourier transform on the ancilla, and that will give you like a root n stronger focused interaction strength. But then you may raise the concern that, well, here for qubits, like after Fourier transform, like I don't know what the outcomes. They are not like qubits anymore. So here's the idea that is, well, we know that the qubits can be approximated by the two lowest energy levels of a boson mode if the state is mainly supported in the ground state and seldom visits the first excitation. Because if the state is mainly here, then it cannot feel whether there are extra energy levels. And this turns out to be the case for our protocol. Why? Because, well, if you look at the Hamiltonian, like in the first slide where we replace the bosons with qubits, you'll see that, well, each ancilla qubit is coupled to this operator. And here T, I want it to be like, let's say, 1 over root n. So it's like the time I want to simulate have one layer of gates. So here naively, you can see that, well, this operator itself like scales as n. So it's like after multiplying with T, this is like very large number. So it may kind of excite my states like in the whole like in the whole qubit subspace, which will destroy the qubit two boson map. But that is not the case for most states. Why? Because here you are basically summing over some independent, so suppose there are ZK that kind of chosen randomly, you are basically summing over n independent variables. So actually, for almost all states, this whole thing at T is this whole thing is actually order 1. And you can do some tricks to kind of to bound the errors more carefully to show that, well, this thing can be much smaller than 1, so that in the process, the states typically only are supported in the ground states, so that the qubits actually work as well as they do compared to the previous.
Sorry, ZK also was on it?
So ZKs are the data qubits, so they are qubits.
They are qubits.
Yes. Okay. I don't care whether they can be bosons.
You don't care if they're bosons.
Yes, these can be like any state in their qubit space.
But they're not bosons.
They're not. So they satisfy like the commuting relations as.
But they're two-level systems.
Yes,
they're not n levels.
Yes.
Because otherwise it would just be coupled harmonic oscillators, and you can't compute coupled harmonic oscillators. Right?
Yeah. Yeah. So the upshot is that, well, it turns out the Fourier modes, you can still view them as working as bosons or even qubits up to very small errors. And I think it is kind of interesting to compare to this spin wave theory in physics, which kind of shares like a similar spirit, which says that, well, even if you start from a system composed of qubits or spins, the lower energy excitations are kind of well approximated by bosonic degrees of freedom. That it's like there are kind of infinite energy levels. And here is a kind of rigorous treatment of that fact in this book. Okay, so finally let me conclude. So I have presented two kind of all-to-all Hamiltonian protocols. First, to show that you can use them to simulate any circuit that is like root n faster than the naive approach. And sometimes you can do even like n times faster, for example, for preparing like a JHC state, W state, etc. And I think for Outlook, I'm kind of mostly excited about whether this can be experimentally feasible. And I think this is like a great place for me to discuss and learn from many of you about this experimental aspects of the problem. So I guess here are just some like very rudimentary my understandings of it. So for example, for Rydberg atoms, probably like we just like they don't have like auto interactions, at least for like very large devices. So people just want to kind of move qubits around by phasors, etc. So probably you don't need to consider that. But there you still have this like routing overhead. So maybe in some systems where you can choose from like either using like gate-based circuits or using auto Hamiltonians, maybe sometimes you want to use like these kind of auto Hamiltonian protocols to avoid such routing overheads, which I don't know may scale like even worse like in larger and larger system sizes. So here for our protocol still is kind of not that easy to establish in experiments because first of all this protocol they have this like complicated JIJ coupling, which is like a phase like a for a transform phase, which I don't know how to like realize using like simple interactions. So it seems like this like n-time faster protocol may be a bit more relevant, where it's basically only use a kind of uniform JIJ. But on the other hand, it requires like a few special qubits that talk to the other like ensemble of qubits, but the ensemble of qubits you know couple with each other in a different but of course throughout this talk I assume like no noise happens, and it is not that clear like with noise probably like one needs to develop like new fault tolerance like schemes to understand like how to correct noise in like Hamiltonian evolutions for that circuits. And as for theory part, I think it's a very interesting question to understand. Well, nowadays many of the devices are kind of analog, so how can we understand the connection between these analog devices versus like digital versions of information processing? And also, I've mentioned this like structure of manifold states, etc. So here we have a better understanding of how fast information can propagate in the system, etc. Does that tell us like more structural properties of long-range interaction systems, for example? And with that, I have to thank you for your attention and happy to take any questions.
Actually, we want to start. Yeah, we should start with.
Thanks for the nice talk. I just want to clarify. So basically, let's say going back to the boson explanation. So my impression is that you actually need like a single boson mode for each qubit in order to achieve the root and speed up.
Exactly. Yes.
And if I only have like a single, like a constant number of boson, then I can only have like speed up on like very specific cases at the general circuit.
Yes. Yes. Exactly.
And secondly, I kind of want to see what's your kind of like connection. So basically, I know that like for some like protocols, let's say preparing symmetric Dicke states and like cavity QE protocols actually give you like a log n, so exponential speed up relative to like a circuit makes one. Could you make some comments?
So what do you mean by magic Dicke states? So I know for Dicke states there are like log n time protocols to produce them. At least when you allow for measurements and feedback.
I think yeah, those are measurement and feedback based one, but this is like just like purely unitary protocol without any measurement.
I see. That's it. So I think in my previous protocol I have this like 1/n time for like W state, which is a special case of Dicke state. I think probably for general Dicke state you can also do in that amount of time. The auto Hamiltonians, but there the question is about, well, you have to prepare a particular Dicke state that you want. You just want to prepare like any Dicke state in this energy window, then I think that should be straightforward. You just kind of at the final step kind of project onto the axilas, and So for a specific liquid state, probably you can do some kind of a binary search to really pin down the one that you want. But I don't. Yeah.
So, you made this comment, so you're using arbitrary end-to-end gates. Do I need to be able to do multiple simultaneously?
Yes. So this is like the second result of that. It's like, well, I have this circuit on the right, which has like simultaneous two qubit gates, and I can simulate these by basically 1/√n time Hamiltonian evolution.
But I guess you're 1/√n time, but at each time step, I have to be able to do an arbitrary number of independent all-to-all gates.
I see. So yes, indeed, you need like order n couplings all turned on with this special coupling form, which is like a phase factor.
I see. So if I can have that one coupling form,
Yes.
where I don't have to be able to do the coupling, just that one form instead of.
You need also a time-dependent version. It's like sometimes you can turn on this, sometimes you can turn on the couplings between the oscillators and another set of n qubits. If you can do that, then and you can tune the time to be very precise. Then you can.
How many control parameters do I?
Basically, like for the simulating one layer of gates, you need to do like a 4-step evolution where each step is a time-independent Hamiltonian evolution.
But it's the same. Basically, let me ask that. Most of these arbitrary types of schemes either give you like an all-to-all with some e to the ikx that comes from the cavity that you're coupled to, right? Or by varying a detuning in the ion chain, you can get a specific connectivity, right?
Yes.
What I want to make sure is that you're not requiring that I be able to do a whole bunch of different many-to-many gates simultaneously. Just having that one shared.
I need basically two versions.
Two versions.
Like basically two sets of couplings. I need to either turn this on or turn this on. And I would think that would be
But
good.
you don't have to turn on both at the same time.
But even both at the same time, I think is okay. Yeah. Right.
I don't think so, because you need to for example, you have to configure your atoms like either phase or population and then use an all-to-all.
Oh, that's what you meant. Yeah, got it. Yeah, sure.
But you can probably.
But you can
do both.
parameterize that.
Yeah.
But what I'm trying to understand is if one superconducting cavity, like Monica Schleiersmith is building up, enough to get this big increase in the power. And I'm asking. I'm not telling you.
I guess the phrasing of the same question is how many different coupling constants do you?
So the constant basically is what is that?
It's fixed.
Basically just for
Fixed, but has n versions.
the value can be like many.
I see. I have to be able to change.
Change the coupling strength from this pair of qubit to this pair of qubit. You need to be specific of this form. A and A are labels of the qubits.
I see. It's like a. Yeah, I see.
Or maybe he.
It's a spin boson coupling between like a real space and a Fourier space.
But it transforms this analysis to the qubit only version.
Yes.
We've been overkill for you.
Yeah. Anyway, I'm trying to keep us on time, so let's thank our